good to go. Should say we are recording. Okay, there we go. So today we're going to start off by looking at table of values and writing rules. We're going to investigate and try to figure out a trick to help us figure out what type of function it is. It's super neat. It's super cool. I love it. And then once we do that, I may toy into graphing those functions, but I want to practice writing those rules. So on standardized tests, the SAT, the ACT, and then later on down the road, you may be given tables and asked to investigate the tables and then identify rules. So sometimes you can use your calculator. You can insert the lists into your calculator and perform regression. So I don't know if y'all have done that before. Since we're without calculators, I'm trying to stay away from using calculators too much and using Desmos when we can. But I want to go ahead and look at some tables. So in particular, let me pull and share my screen with you. I want to look at two tables. So here we are. So I want you to look at these two tables, and I am throwing in a lot of things that weren't necessarily in the packet because I think, I'm kind of sharing things with you based on your feedback and what you seem to maybe need a little bit of practice on. So I kind of made this up this morning. And we have two tables, and we've talked about how to start investigating the data in the tables to help us determine the rule, if we can. So the first thing, if you're given a table, the first thing you want to do is ask yourself, is it a function? And since we've talked about the definition of a function a lot, and we looked at the different representations and how to help us determine if it is a function, can you look at these two tables and first tell me, are they functions? So looking at these two tables, do they represent functions? They're relations because they have input and output, domain and range, X and Y, but are they functions? Yes or no? Anybody?
Yeah.
Yeah, they are. And how do you know they're functions?
None of them repeat.
None of the X values, be a little bit more specific, Gabriella. None of the X values repeat with different Y values. So I know what you meant, but when you state it, I'm just getting you ready in case maybe you take the AP exam as well. You have to justify how you know things. So in this case, you are absolutely correct, Abiela. None of the X values repeat with different Y values, so they are functions. So the next step would be to maybe try to figure out what type of function it is. So again, there's different ways to represent different types of functions. We've talked about one, kind of hinted on two, and hopefully we'll explore a lot of other families. But if I'm looking at this table, what might you do first to maybe see if it's one that we're very familiar with? What would you do first? What's your gut instinct to do first? Anybody? I see Eric's going back. Eric's going back and looking to see if he can help us. Go ahead, look and see. What did we do with some past tables of values to help us see if there was a pattern?
I was thinking the finite differences.
Yes, absolutely correct, Eric. I am going to look at my change of Y, and we called that our first finite difference. And that's exactly what your go-to should be. That is a great first way to check. So if I look at my change of X's, I see that they're just consecutive integers. So the difference is 1. So I don't really have to focus on that. So now let's look at our first finite difference. So if I take -8 minus a -5, what is that difference? Do we know? -8 minus a -5. So that minus a minus, right, becomes plus. So what's the difference?
3.
What is it?
3.
Is it +3 or -3? What do I have more of? -8 and +5.
-8.
-3. Okay, Christopher chimed in. Christopher chimed in chat. So he's unable to talk because he's actually somewhere in another class, but he's in our class at the same time. So Abiela, do you see if I'm on the number line? Christopher, you're absolutely correct. If I'm at -8 and I add 5, I'm at -3. Do we see that if I look on the number line? So -8 plus 5 is -3. What about -5 minus a -2? What's that difference?
-3.
Yes. Okay, what about -2 minus 1? What's that first finite difference? -2 minus 1.
Oh wait, that's positive.
Okay, well, Christopher's chimed in, but let's look at it. And Christopher, you are correct. If I'm on the number line at -2, right? -2 minus 1, can't I write that as -2 plus a -1? So -2 plus a -1, so I'm going more in the negative direction. That's also a -3. Abiela, do you see that? Are you sure? Nathan, do you see that? I mean, are you getting this arithmetic?
Yes, ma'am.
All right. What about 1 minus 4? What's that difference? 1 minus 4. If I'm at 1.
-3.
If I'm at 1 and I go back in the negative direction, 4.
-3.
-3. Yes, -3. All right, there we go. And what about 4 minus 7? 4 minus 7.
-3.
Again, -3. So now that we've calculated our first finite difference for every set, every pair of consecutive points, right? Since that is constant, since we have a constant first finite difference, what can you tell me about this function? What type of function is it? Since we have a constant first finite difference, also known as a constant, this is a hint, rate of change, constant rate of change, what type of function is this? If I were to plot those points and connect them, what graph would I see?
A linear equation.
It is a linear function. Yes, it is linear. So if you have a constant first finite difference, it is linear. And since it's linear, I can write the equation, and I can write it in slope-intercept form, or if I write it in terms of A and B without the M. So A is M, right? Those are the same equations. It's just whether I represent the slope as M or the slope as just the coefficient of X, which is A. From this table of values, what does this -3 represent in this equation? What does that first finite difference, that constant rate of change, represent in this equation?
The y-intercept.
Not the y-intercept, but we can get that from the table. But what does this -3 represent?
The slope.
The slope. So this is your slope. So we can call that M, or I can call that A. So M or A, it doesn't matter which letter you use, it's your coefficient of X. So if you have a constant first finite difference, you know that it's linear, and this number here, this constant rate of change, is your slope. You're rising and running well, actually you're falling and running. -3, down 3 over 1, down 3 over 1, down 3 over 1. So that is your slope. So I can start writing the equation, but I need that B. Now, in the table, sometimes it's given, or sometimes you have to use the pattern we recognize to be able to get this value in the table. Where can I look in the table to find the B? What does the B represent in the equation?
The y-intercept.
The y value of the y-intercept. Eric, you are correct. This is the y value of the y-intercept. Now, if it is a y-intercept, it's falling on the y-axis. So what do we know about all points that fall on the y-axis? They have the same x value. What is that x value? If I'm on the y-axis, what is the x value?
0.
0. So I can go to the table for when x is equal to 0, and that y value is your B. So I can take this 7 and I can substitute it in here. And then I have the equation of the line. So the coefficient of x is your slope, your constant rate of change. We see that in the table as the first finite difference because it's constant. Does everybody see how to get that rule? Yes? Any questions on that? Because we're about to move away from this. But we needed to refresh our memories about this. And then, of course, if we really wanted to graph this, we would take this y value of the y-intercept, and then we would rise and run the slope. Right? And that's how we'd get the graph. Okay? Now, what I want you to look at, so we said this was A. This was A, your slope, the coefficient of x. I'm just going to let you explore this one. I'm not going to derive it for you. Let's see if you can come up with it. What I want you to do now is I want you to look at this table of values. You said it was a function. My question to you is it representative of a linear function? Is it linear? You tell me, is it linear? And how are you figuring that out? I see pencils moving. What are we trying to do? What are we doing to figure out if it's linear? Natalie, Nathan, what are you doing? What are you trying? How are you trying to figure out if it's linear? What are we doing? What are we calculating?
The slope.
You're trying to see if it has a slope. Yes, Nathan, you are correct. So you are calculating your first, and I'm going to abbreviate it as FD, finite difference. So that's the first thing that you should do. You are looking at the finite difference and you're trying to see if it's constant, because if it's constant, it's linear and we can go through the same process we just did. So let's do the subtraction. 163 minus 111 is what? Oh my goodness, we can do the subtraction.
52.
52. 111 minus 69 is what?
42.
Uh-oh. 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 We know automatically, right? We know immediately, right? Because this change in x is 1, right? So since that 1 is 1 and those two numbers are not the same, what can you tell me immediately?
It's decreasing by 10 on slope.
Okay, well, but you can tell me it's not linear, right? I mean, since that number is not the same, it's not a constant rate of change, it is not linear. Do you see how immediately I can tell it's not linear? This is not a line. If I were to graph this, these points would not fall on a line. So we're using process of elimination. So we're going to go ahead and continue. Eric, you are correct. If you continue the subtraction, you're going to get this, right? So there's your first finite difference. We notice that those numbers are not all the same. So immediately you can say it is not linear. But is there another pattern we see so that we can deduce, we can determine that it is another type of function? So what would you do next, maybe? Well, after you realize the first finite difference is not constant, maybe you calculate the second finite difference. Meaning you're going to subtract the difference of the differences. And Eric already told us that the second finite difference, if we do the subtraction, was what? Eric, tell me again.
There's a difference of 10 in between
Between the differences, right? So our second finite difference is constant. So since the second finite difference is constant, that is your clue that it's another type of function. Does anybody know what type of function it is? And I don't really necessarily expect you to if you've never investigated finite differences. So, in the first one, we found a constant rate of change because the first finite difference was constant. We knew it was linear. We could substitute in the slope and then look at the table and find the y value of the y-intercept. We could write the rule. However, this equation is not linear. So take a minute and see if you can come up with a rule. What are you doing to x to get y. Now, I don't necessarily expect you to figure it out. We said this number equals a. If I were to plot those points, I wonder what that would look like. What would it look like? What type of equation would it be? Any ideas? If I were...
I think it could be exponential. I'm not too sure.
Well, there's a different pattern that we would recognize if it was exponential. So I'm going to say, Eric, no, it's not exponential. However, you are noticing that it looks like that a little bit. Is that what you're saying? So your first instinct in looking at that graph would be maybe it's exponential. Well, what would happen if I were to back up the pattern, right? Where would it go? So, I mean, I could test it and I could say, all right, that would be, if I subtract 10 from 12, that would be 2. So when x is -1, y is 2. Well, I'll tell you what type of function it is, but I'm not going to tell you what the 10 represents. The type of function, if you have a constant finite difference for the second finite difference, so a second finite difference that is constant, that means it is quadratic. Eric, that's part, right? That's the up part. We're just not seeing the other part. So if you have and again, let me reiterate this. If you have a second finite difference that is constant, it is quadratic. So can anybody tell me what the equation in general form of a quadratic equation is? If this is a linear equation in standard form, what would the quadratic equation be in standard form? Abiella, are you looking like you're going to tell me?
I don't know if it's right though.
Go ahead. We'll find out one way or another. What do you think?
10x squared.
Okay, don't put any numbers in there. Just give me the general form. You kind of already hinted.
Sorry.
You already hinted.
Let's see. Sorry.
So if this is the general form, slope-intercept form, actually, slope-intercept form of a linear function, what would a quadratic equation look like in standard form? You already told me I had an x squared. That is correct. But that would be ax squared plus bx plus c. Have you seen this? You've seen this equation, right? So, Abiella, you were already trying to write the equation. And so, again, we calculate finite differences. If it has a second finite difference that is quadratic, that is constant, I know it's quadratic and I'm going to use this formula. The question is, how do I use that 10? So, Abiella, you're telling me the 10 is the A. I'm telling you, not quite. But the 10 is going to help you find the A. How? I'm not going to tell you. I'm going to let you derive it. So the first step is, we're given a table of values. We start calculating finite differences. That's what we start calculating. This is the process you're going through. These are the conclusions that you're making. Given a table of values, you first check to see if it's a function. Then you start calculating finite differences. If it has a first finite difference that is constant, it is linear. This number represents the slope, the A. If it has a second finite difference that is constant, it is quadratic, but we don't know what that number is. It's not A. How are we going to figure out what it is? I'm going to begin with this equation. So let's get ready. Are we ready? Are we ready? Here we go. I am going to take that quadratic equation. So y equals ax squared, and you're going to derive it. You're going to tell me what that 10 is. You're going to tell me. I'm not going to tell you. You're going to derive it. We are taking this quadratic equation. So everybody write down the quadratic equation. Y equals ax squared plus bx plus c. Then we are going to kind of create a little table. So I'm going to first let x equal 0. If I let x equal 0, and I'll do the first step for you, I'm going to substitute in 0 for this x. So everywhere I see an x, I'm going to substitute in 0. Now, if I do that, look what happens. This goes to 0, this goes to 0, and what am I just left with? I'm left with C, right? Does everybody see that? I started with the quadratic equation, and I let x equal 0. When x equals 0, y equals c. Now that makes sense because in our table of values, when x is 0, c is my constant. C is the y value of the y-intercept. So that c value in the table, that y value of the y-intercept is going to be substituted in for that constant c. Does everybody see what I did there? Yes? Okay. What I want you now to do is I want you to do the same process, but now let x equal 1. Then I want you to let x equal 2. Then I want you to let x equal 3. Then I want you to let x equal 4. Then we are going to write the equation, right? You're just substituting in, and then you're telling me what that equals. Tell me what that equals. Tell me what that equals. So go ahead and do that first. Take the quadratic equation, substitute in for the different values of x, and tell me what you get here. So go ahead and do that now. We're going to derive this. I will write it while you're doing it, but don't look up and peek until you think you got it. All I'm doing is substituting in values of x and simplifying. Nathan, we are deriving what the second finite difference is. So we're starting with the quadratic equation. And in the quadratic equation, we're letting x equal 0, x equal 1, x equal 2, all the way up to 4. And then we're simplifying and seeing what we get for the output by letting x equal these different values. So I've written it out, but y'all are actually working out what these are going to be. Does that make sense? Okay, so go ahead and tell me what those would be. The first one we see is C. You are deriving what the second finite difference is so that we can start writing the equation. Do we think we got it? What did we get for the second one? When we substituted in 1 for x, what was the output? Can anybody tell me? Nobody can tell me? Are we still so busy figuring the other ones out? Eric, did you get it?
I think it's A plus B plus C.
You are correct. A plus B plus C. Does everybody see how if you substitute x equal 1 into the quadratic equation, we got A plus B plus C. 1 squared is 1 times A is A. 1 times B is B, and then C. So my output when my input is 1 is A plus B plus C. Can somebody else tell me what we would get if we substituted in 2 for x? What did we get? Natalie, did you get it? Ariana, did you get it? Nathan, anybody? If you let x equal 2 in the quadratic equation, what do we get?
4A plus 2B plus C.
That is correct. Does everybody see how the output, when the input is 2, when x equals 2, that's what we get? Yes? I mean, speak now if you're not getting this, because this whole derivation will fall apart if you don't understand the pieces. Abiella, does that make sense? Okay. Can you tell me then, Abiella, what we would get if we let x equal 3?
Um, 6A plus
What's 3 squared?
2.
3 times 3 is...
Oh my god.
That's okay. It's okay.
Um,
What do we get?
9.
Yes. So 9a, okay, plus?
3.
Yes, 3b plus c. Yes. So that is the output when your input is 3. Natalie, Nathan, Ariana, can somebody tell me what my output is when my input is 4?
16a plus 4b plus c.
Oh, that is fantastic. So now that is beautiful. Thank you. So now we have a table of values. Yes, they have variables, but there's nothing wrong with that. We have a table of values and we can start calculating finite differences to see what that second finite difference is. So let's start, and then here we go. So our first finite difference, here we go. We are subtracting. If I take 16a plus 4b plus c, so if I take this and I subtract that from it, what do I get? So 16a minus 9a. Nathan, what is that? 16a minus 9a is?
7a.
Is that correct? Yes, it is. And what about 4b minus 3b?
B.
Okay, and then c minus c?
0.
0. So does everybody see how the first finite difference is 7a plus b? Now, we know this is quadratic, so I know that that next difference is not going to be 7a plus b. So tell me, what is the next difference? Nathan, tell me what the next difference is.
5a plus b.
And keep going.
And then it's 3a plus b.
And then?
AB.
A
B.
plus B. A plus B. Very good. Very good. So we have taken the quadratic equation. We have evaluated it at different values of x. We got a table of values. We found the first finite difference. Now, if this were linear, our first finite difference would just be A, but it's not. So can you go one step further and find me the second finite difference? And tell me what the second finite difference is. You do the subtraction. So this minus this, this minus this, this minus this. Tell me what that second finite difference is. This is so exciting, the big reveal. Do we have the second finite difference?
There's a difference of 2a in between each.
Every single one of them is 2a. That is absolutely correct. So that is telling you, can everybody see how this is 2a? 7a minus 5a is 2a. B minus b, gone. 5a minus 3a is 2a. B minus b is gone. So this is telling you, you have just derived what the second finite difference for every quadratic equation is. It is 2a. For a linear function, the first finite difference is a. For a quadratic function, the second finite difference is 2a. Before I move on, can everybody see the 2a? If not, speak now or forever hold your peace. Okay, you have just derived the second finite difference of a quadratic equation to be 2a. So now let's go back to this table here. We said it was quadratic, right? We said this one was quadratic. It had a second finite difference that was constant. So that is telling you that 10, that second finite difference that is constant, equals, what did we just derive? We said it equaled what? Well,
2a, sorry.
2a. Whatever number you get for a constant second finite difference, you set it equal to 2a. So what does that mean? You can tell me what a is. What is a?
A equals 5.
Yes! A equals 5. Now, that is fantastic. Look at us writing this equation. Look at us writing this equation. If you can calculate the second finite difference and get it to be a constant, you know it's quadratic. You know that whatever number that second finite difference is equals 2 times the value of a, the coefficient of x squared. We have found a. Is there anything else from this table that you can tell me about this equation? Is there any other value I can substitute into this equation?
You could probably find b too.
We can find b, but is there anything? Yes, we will. But is there anything from the table that will allow us to immediately substitute into the equation?
C.
Yes. How do I know what C is? How do I know? And if you need a little refresher, what did we say C was?
C is the y-intercept.
C is the y value of the y-intercept. So C is the output when our input is 0. So what is C? C is
3.
3. Look at us. Look at us writing this equation. So I now have y equals 5 x squared plus bx plus 3. All I have left to have the equation, all I have to find is b. We're going to do this the same exact way. We found b for a linear equation. What did we do to solve for b? What do I have at my disposal? What can I use to help me find b? I have a whole table of values, don't I? Can't I just pick one? Can't I just pick a table of values? That's an x and a y. So can't I just substitute in x for 1, y for 15, and find b? Do you see how I've done that? I just pick a point. I know that point's on the graph of the equation. So I can just substitute in the x and the y value and solve for b. Do you see how I'm doing this? Does this make sense? You're going to have to do this for an entire sheet of tables. So if it doesn't make sense, now's the time to say something. Okay, so what would B be? What would B be? If I solve for B in that, what would it be? What's B?
7.
Yes, it is. Right? So B is 7. So now I can come back in here and I have my equation. Look at that. That's fantastic. I mean, you got to admit that's look at that. From a table of values, you can write the equation. Now for a linear and a quadratic, there are different things that you will recognize in the table for different types of functions. Right now, we've talked about linear and quadratic. There are other patterns that you will see for other types of functions. Now, guess what we're going to do next? We are going to go to our guess and check patterns. You see this sheet in your packet? The first thing I want you to do, you see this? Does everybody see this sheet? Yes? Nathan says yes. Eric says no. Everybody else, we see it. Natalie, we see it. Abiella, yes. Ariana? Okay. I want you to look at these tables, these T tables, and I want you to first determine, this is what we're going to do first, before we start writing rules. Is it linear, quadratic, or neither? It may not be either one of them. So the first thing you're doing is you're looking at finite differences. So use finite differences, whether it's first, second, whatever. Use finite differences, and determine, is it linear? Is it quadratic? Is it neither? So I want you to write on every single one of these, I want you to just write linear, what is it? Linear, I'm not even going to write it there. But, next to it, write L, Q, N, I don't care. First, go through all of the tables and determine if it's linear, quadratic, or neither. We will go over that because I don't want you to try to find rules and the wrong rules, right? So let's first determine which they are. And then once we have identified what they are, if they are linear or quadratic, you are going to write the rule. If you get stuck, talk to each other. I'm not going to say anything till we go over it. So you're looking at X and Y, and you're calculating the first finite difference, and then if necessary, a second finite difference. I'm not going to say a thing until we check them. And then you're going to write the rules. And they may be neither. They may not have a first finite difference or a second finite difference, in which case you cannot find it right now. If you get stuck, say something. Are we able to recognize them? Can we determine, are we having luck? Are we getting them? When you think you have determined whether it is linear, quadratic, or neither, raise your hand in teams. If you feel confident, go ahead and start finding the rules. Linear, y equal mx plus b. Quadratic, y equal ax squared plus bx plus c. Neither, there's nothing you can do. Once you have determined if it's linear, quadratic, or neither, if you want to take a tiny break and you need to use the facilities or get water, you may. If you have any questions, vocalize them. I'm going to use the facilities. I'll be right back. Feel free to discuss with each other if you're stuck. Again, raise your hands once you've finished determining what type of functions these are, if they are. Once you have determined if they're linear, quadratic, or neither, raise your hand in teams. And we will go over them first. And then you can write the rules, unless you are confident, in which case you can just go ahead and write the rules. Are these difficult or are we getting them? Have we got, how are we coming? What number are y'all on? Nathan? Eric, what number? Abiella? Christopher?
14.
I'm on number 7.
Number 7, number 14, okay. Natalie,
6 more to go.
you have 6 more, okay.
I'm on 11.
Are we feeling confident?
A little bit, yeah.
Okay. It's an exciting moment of truth. We're going to go through them, and then you're going to find the rules. And then maybe we will even touch on graphing 1 or 2 of these, Nathan, of the quadratic ones. If you get stuck, ask me a question. Once you've finished, raise your hand in teams. Feel free to go ahead and try to find the rules if you think you can, or if you want to wait until we go over what they are, that's fine too. The linear ones, you should definitely be able to find the rule though. Ariana, did you get them?
Yeah.
You think you got them all?
Yeah, but now I have to find the equation.
Okay, go ahead if you want to get started on those. Go ahead, go right ahead. Abiella, did we finish? Once you finish figuring out whether they're linear, quadratic, or neither, raise your hand so that we can go over that. But go ahead and feel free and start finding the rules if you determined the nature of them. Okay, so Ariana has determined all of them. Natalie thinks she's determined all of them. Natalie, go ahead and start finding the rules. Nathan thinks he's found all of them. Go ahead and start finding the rules. And as soon as everybody's gone and able to determine each of them, we will go over them. But Nathan, go ahead and start finding the rules for the linear and the quadratic. Okay, Eric thinks he's found them all. So we're waiting on Abiella and Christopher. So when y'all think you got them, raise your hand and then we will go over them. In the meantime, those of you who have found out which they are, go ahead and find the rules. Abiella, how we coming? Christopher, how we coming?
I have to.
What was that, Abiella?
I have 6 more.
Okay, you just keep on working. Christopher, I see that you think you got them all, so let's go ahead and find those rules. If you get stuck writing the rules, you can ask each other for help, or you can check your answers with your math friends in here.
Linear?
Linear?
It is. And what is the first finite difference?
11.
11. Okay, so you're good to go. The second one, is it linear, quadratic, or neither?
Linear?
It is linear. And what is the first finite difference?
8.
8. Excellent. Number 3, linear, quadratic, or neither?
Linear.
It is linear. And what is the first finite difference?
7.
7.
Excellent. Number 4, linear, quadratic, or neither?
Neither.
It is neither. There is not a first finite difference or a second finite difference. So as of right now, we cannot find the rule. We leave it alone. Number 5, linear, quadratic, or neither?
Linear.
Linear?
It is linear. And what is the first finite difference?
7.
7. Excellent. So if we have the first finite difference, we have M or A, depending on how you can work it. And you can write the rule, right? Because we can find that Y value of the Y-intercept in there. What about number 6, linear, quadratic, or neither?
Linear?
And it is. And what is the first finite difference?
7,
7 again. What about number 7? Linear, quadratic, or neither?
Neither.
It is neither, so no rule for that. Number 8, linear, quadratic, or neither?
Linear.
It's linear. And what is the first finite difference?
-3.
-3. Number 9, is it linear, quadratic, or neither?
Quadratic.
Number 9 is quadratic. And what is the second finite difference?
2.
2. Excellent. Excellent. Nathan, are you getting these? You're not saying anything. Are we getting? Number 10, linear, quadratic, or neither?
Quadratic.
It is quadratic. And what is the second finite difference?
2.
2. Excellent. Number 11, linear, quadratic, or neither?
Quadratic.
It is. And what is the second finite difference?
6.
6. Excellent. Number 12, linear, quadratic, or neither?
quadratic,
Excellent. And what is the second finite difference?
10,
10. Beautiful. Number 13, linear, quadratic, or neither?
neither,
It is neither. No rule to find right now. Number 14, linear, quadratic, or neither?
quadratic,
Excellent. And what is the second finite difference?
2,
Beautiful. Number 15, linear, quadratic, or neither?
quadratic,
Excellent. And what is the second finite difference?
2,
Beautiful. Number 16, linear, quadratic, or neither?
quadratic,
Excellent. And what is the second finite difference that you found?
it was 2,
Beautiful. Number 17, linear, quadratic, or neither?
neither,
It is neither. No rule to find. And Nathan, number 18. What is number 18? Linear, quadratic, or neither?
Quadratic.
It is quadratic. And what was the second finite difference?
I got 5.
For the second finite difference, when you did the first finite difference, you got numbers that were not constant. Then you did it again, right? So what was the second set of differences? Not 5. So if I subtracted here, right? We got 52, 42, 32, 12, 22, 12. And then the second finite difference was what?
10.
10. So the second finite difference is 10. Okay, so y'all are pretty good at determining whether they're linear or quadratic. So the next step is finding those rules. So let's find those equations. Let's write those rules. If you finish that, or when you should, I shouldn't say if, you're gonna finish it. When you finish that, raise your hand, and then I would like you to tell me what you think the third finite difference is going to give us if it's constant. What type of equation and what does the third finite difference represent? So that's a little extension if you think you can figure it out, right? So first finite difference constant, we said it was linear, and the first finite difference was A. Second finite difference was constant, it was quadratic, and it represents 2A. Third finite difference, if it's constant, what type of equation is it, and what does it represent? That's after you find the rules. So let's find those rules for the linear and quadratic ones. Raise your hand when you finish, and then try to figure out what the third finite difference is. Different type of equation. So I'll let you work. If you get stuck or have a question, ask it. When you think you have all the rules, go ahead and put your hand up in Teams. Okay, Eric, you can go ahead and try to figure out, and I'll give you a hint, the way we let x equal 0, 1, 2, 3, 4, etc. in a quadratic equation. Try to think about what a third finite difference would be.
I was thinking, since like the first finite difference is linear, and the second is quadratic. It kind of goes from one dimension to two dimensions.
Well,
So I was
they're all in
thinking
two dimensions. We're only in two dimensions, right? We're only in X and
Mhm.
Y. So our
Yeah, so that's why I was thinking of if the third one would probably go into would probably be cubic equations.
a cubic equation.
Yeah, because it would be taking into account a different kind of dimension. That's the way I was thinking about it, at least.
Well, okay, be careful what you're saying.
Mhm.
What you're saying, I know what you're trying to say. And the fact that you said a third finite difference or a constant third finite difference would make a cubic equation, that is correct. So what would the equation be? What is the standard form of a cubic equation?
I'm not even sure if I remember.
And how would we, so for a linear equation, the highest exponent was 1. For a quadratic equation, the highest exponent is 2. So for a cubic equation, the highest exponent would be
3.
3. So this would be the standard form, right?
Mhm.
Okay.
Oh yes. Okay.
We're still in two dimensions, right?
Mhm.
I mean, two dimensions means we're graphing on the Cartesian plane. We haven't left and gone to 3 space, or else there would be a z, x, y, z, right? And it would be an order triple. So this is beautiful. Third finite difference is constant. It is cubic. There is the equation of a cubic function. Now, what does that third finite difference represent? Take this equation, let x equal 1, 2, 3, 0, 1, 2, 3, 4, 5, 6.
I wonder if it represents the exponents.
Now, I'm not going to tell you. Do you? I mean, that's for you, my dear, this is for you to figure out. So you remember how we took this equation and we let x equal 0, x equal 1, x equal 2, x equal 3, and we found the first finite difference and we found the second finite difference, and we said the second finite difference was 2a. Now take this cubic, do the same thing, and find the third finite difference and tell me what it is. Derive it. Eric, you can do it. Eric, derive it. Derive it, Eric. You can do it. But you are correct. But it's still two dimensions, so be careful. But it is a cubic function. Eric, derive it. Get a piece of paper out and derive it. Derive it. You can do it. Derive it. So substitute, you see what I'm saying? Substitute in 0 for x, then 1 for x, then 2 for x, then find the first finite difference, and then find the second, and then find the third, and tell me what that is. Make sense? You can do it. You tell me. You derive it, Eric. Derive it, Eric. Everybody else, let's find those rules. Let's find those rules so we can go over them. Eric, you gonna grow up and be a little mini mathematician?
I'm aiming to be an engineer.
An engineer,
I'm not sure
you need math for engineering. This is good.
Yeah, you do.
This is good for you. This is good for you. The rest of you, you're gonna be little mathematicians now. I hope y'all all turn into little mini mathematicians or engineers. Something in STEM. Christopher, are you getting these? You getting the rules, Christopher?
Yeah.
It's making sense?
Yeah, it is.
Okay. Natalie, how we coming? We getting the rules? Kind of, hopefully. Kind of, okay. If you get stuck, let's communicate. Ariana, how are we coming? We feeling comfortable with the rules?
No.
No,
Not on the quadratic ones.
not on the quadratic ones. Okay. So what in particular? So let's look at number 9. So do we remember for a quadratic function what we always set the second finite difference equal to? What did we derive? What did we say that represented in the equation? I can't hear you. You're moving your mouth and I can't hear you.
I'm not too sure.
Okay. Can anybody help Ariana out? What did we say that the second finite difference represented in a quadratic equation? We derived it. Nathan, Christopher, can anybody help her out? What did we say we set this number, the second finite difference, equal to? We derived it.
It was equal to A.
Not A. For a linear function, it was A. For a linear function, it was A. For a so a linear function, the first finite difference is A. For a quadratic function, remember, for a quadratic function, we derive the second finite difference to be 2A. Right? 2A, right, Christopher? 2A. Ariana, do we remember?
Yeah.
Okay, so if that equals 2A, then we come back to our table and we set that second finite difference equal to 2A. If I set that equal to 2A, what is A in this one? If I solve for A, if I set 2 equal to 2A, I divide both sides by 2, and what is A?
1.
1, right? Christopher, you see that? Nathan, you see that? Natalie,
Yeah.
you see that? Okay, so if I'm trying to write a quadratic equation, right? y equals ax squared plus bx plus c. I know no a, right? So that's 2x squared plus bx. And do I know what c is from the table? Can you tell me what c is? What does c represent?
0.
It represents the output for when the input is 0. So in this case, c is 0. So all I have left to do to finish writing the equation is I have to figure out what b is. So how am I going to figure out what b is? What do I do? How do I find b? Nathan? Christopher? Anybody know? How am I going to find that b?
You use one of the points?
Yes, you use one of the points. So it doesn't matter which point you use. So, I mean, I like to work with the smallest possible. I mean, obviously I can't use 0. So here I have an x. When x equals 1, y equals 3. So I'm going to substitute in 3 for y. I'm going to substitute 1 in for x. And I'm going to find b. So what is b? Do we know? Oh, I've substituted in 2 for, nobody said anything. Oh my goodness gracious. That's a 1. Nobody said anything. Right? So I substitute in 1 for a. And then I substitute in 3 for y, 1 for x. And again, there's no 2 here. That's a 1. And what is b? Do we know what b is on number 9?
Would it be 3?
Not 3. So let me substitute in again. I have 3 equals 1 squared times b times 1. So 3 equals 1 plus b. So what is b? Natalie? Abiella? Anybody?
Would it be 2?
It is 2. So then I can come back in here. And I don't need that 1 there. And I have my answer. So y equals x squared plus 2x. Ariana, does that make sense?
Yeah, it does.
Shall we talk about number 10? Because we said that was quadratic. And just go through one more. Okay. So what do I set this equal to?
2a.
2a. So what is a?
1.
Right? Okay. So I have, oops. Let me erase this. So a is 1. So if I start writing the equation, I have y equals 1x squared plus bx. Do I know what c is?
And 0.
Yes. So c is 0. I don't need to write it. So now I'm going to take any point other than the input being 0, and I'm going to substitute in 1 for y and 1 for x, and I'm going to solve for b. So what is b in this case? What is B?
Zero?
Yes, B is 0. So this is gone. So what is the equation? Just y equals x squared. Does that make more sense? A little bit? Natalie says yes. Ariana says, okay. Nathan, yes. All right, let's get those rules. Let's write those rules. See, you got to speak up. You have to say something if something is stuck. Don't just sit there suffering. Okay, so let's write those rules. Abiella, now that you've completed all of them, why don't you do what Eric's doing? Let's look at the cubic equation and let's try to figure out what the third finite difference represents in a cubic equation.
I think I just found it, but go ahead and I'll say it.
Why don't you type it to me privately and I'll tell you if you're right.
Okay, got it.
Abiella, go ahead and try to figure out what the third finite difference represents. And Eric, tell me what you think the third finite difference is. Send me a chat. In terms of A, right? It's not A, it's not 2A. What is it? You gonna send it to me, Eric? I'm waiting. I'm excited.
Okay, just sent it.
Okay. Why didn't I get it yet? How come I haven't gotten it? Oh my goodness. You sent me a chat?
Yeah, I did. I sent it to. Oh, I think it's because I sent it to the guest.
Oh,
Yeah.
oh yeah. No, don't, because I have two versions of Teams, so I can look at both screens.
Okay, I'll send it to the other one.
Okay. Time to know. Oh my gosh, you got it. How come I didn't get it yet? Oh my gosh, this is so disappointing. Oh. You got it! Oh, wow.
All right.
Oh, wow. You got it. Wow. Good job. You just derived the third finite difference for a cubic function. Eric. Wow. That's impressive. Now, I want you to think about, without deriving, and I doubt you'll figure this out. Without deriving the fourth finite difference, do you think you can figure out what it is? So Natalie, you've gotten all the rules. Go ahead and try to figure out what the third finite difference would represent. Again, we would do it the same way we did the second finite difference, by taking a cubic equation and letting x equal different values and then calculating the third finite difference. Same thing with you, Abiella. You're trying to figure out what the third finite difference is. Eric, try to figure out what the fourth one is without deriving it, but if worse comes to worse and you can't think of it, derive it.
I think I might know. Can I just say it?
No, not out loud.
Okay, got it.
Oh, spoil a surprise for everybody. You send me a chat? No. But I love that you
Dang.
go ahead, derive it. You can do it.
Okay, got it. I keep thinking about it. I'm trying to think of a pattern that's going on in between the second and the third.
Yeah, it's something you probably have never seen before, and I will share that with you, the shortcut, so you don't have to derive it every time on the test. But I'm not going to tell you just yet.
Okay, got it.
So everybody's working on writing rules for the guess and check patterns. When you finish, raise your hand, and by all means, try to figure out what the third finite difference would represent for a cubic, or a fourth finite difference for a quartic, or a fifth finite difference for a quintic. There's a trick, and I will tell you the trick, but not just yet. Ariana, Christopher, and Nathan, do you think we'll be able to go over the rules before we leave today? How are we coming on finding the rules? Are we making progress?
Yeah, I think I get it.
Okay. Do you think we're going to be able to finish before class is over to go over them, or we're going to need to work on them tonight?
When class is over?
Class is over 11:30, so we'll be able to go over before then. Nathan, how about you?
Probably.
Probably. Okay. If not, I mean, we can go over them at the beginning of class tomorrow. That is fine. But I would like to bring it to closure today so we can move forward. But I'm not going to rush you because I want you to understand it. Natalie, Abiela, do you think you figured out what the third finite difference is? Okay, Nathan, try to figure out what the third finite difference is. The third finite difference represents in a cubic function. So we're looking at the cubic equation. We're letting x, we're deriving the third finite difference. Tell me what you think it is. When y'all think you have the third finite difference, go ahead and send me a message. I've put up the answers for the linear equations. So feel free to check your answer for the linear equations. And if you have any questions, ask me. So feel free to check your answers for the linear functions. I have written those. No. Nathan, the finite differences are always going to give you information about A. So the first finite difference told us that it was A. The second finite difference told us it was 2A. So go ahead and try to derive what the third finite difference would be in terms of A. So it's going to tell you something about A. The first finite difference was A. The second finite difference was 2A. What is the third finite difference? Does that make sense? No, it's not. Christopher, derive it. But that is a very logical conjecture. Okay, shall we go over the quadratic equations? Because it looks like we've gotten them, yes? Okay, so number 11. What did you get for the equation for number 11? Somebody tell me what they got for the equation for number 11. No, Nathan, it's not 4A. Derive it.
I got 3x squared.
Y equals 3x squared. That is correct. You're fantastic. Very good. Number 12, what did we get for the equation? Y equals?
5x squared.
That is absolutely correct. Number 14, what did we get as the equation?
I got x squared plus 10x.
I didn't get 10x. Did somebody get something else? For number 14? Anybody get anything different? Well, let's go ahead and substitute in. Let's work it out together. C is 0. So if I choose 4, right? You see how I'm substituting in that 0.14 to get B? What is B?
3.
B is 3. So the equation is y equals x squared plus 3x. Make sense?
I was looking at the other one when
Oh my goodness!
I.
Oh my goodness. Okay, so give me the equation for number 15. Y equals
X squared plus 7. X? 7.
7x. That is correct. That is correct. Okay, what about number 16? What is the equation for number 16?
Y equals x squared plus 5x.
That is fantastic. And last but not least, number 18, which should look a little familiar.
Y equals 5x squared plus 10x.
Not quite. I know C is 3, right? Don't I know that? I know A is 5. I know C is 3. Isn't that true? Okay, so then I can pick a point. It doesn't matter which point you pick. If I pick this and substitute in 15 for Y and 1 for X, what is B?
7.
7. So then my equation, and we actually did this one. Oops. Now, are there any questions? I mean, obviously with more practice, you get better, right? So are there any questions on how to do these? Do we feel comfortable minus a few careless mistakes when we substitute in? Do we understand the process a little bit better? Okay, so given a table of values, you should be able to determine whether it's linear or quadratic or neither. And then again, for the second finite difference, we know it to be 2a. The third finite difference, did we derive that? Are we able to determine what the third finite difference is? Eric did. I'm not going to tell you. I want you to derive it. I want you to tell me what the third finite difference is. Try to figure that out. And then I'm going to give you the shortcut, the trick, first thing tomorrow. There's a trick. No matter what the power of x is, I can tell you a very fast, easy way to tell you what this third finite difference is. Okay? So I'll give you that trick tomorrow. I do want to maybe graph one of these quadratic functions. No, Christopher, it's not 2b. It's with respect to a. There's going to be an a in here. We just don't know what that number is. So derive it. You can derive it. We derived for quadratic. Then we're going to graph one, because you should be comfortable graphing. And then we're going to move forward talking about transformations. And then we'll look at another type of function and be able to recognize a pattern with that type of function. Okay? But I want to leave you with another one of those little picture puzzles because it was so cute yesterday. No, it's not 1/2 A. It's Christopher, stop guessing and just derive it, for heaven's sakes. Here we go. Tell me what the sum in the last row is. And be careful. And we'll end with that. So you tell me. So you'll tell me how much the red flower is worth, how much the blue flower is worth, how much the yellow flower is worth, and then you'll tell me the sum. I think this one is easier than yesterday's because it's all addition and subtraction. When you think you got the answer, raise your hand. Okay, Abiella has the answer. Natalie has the answer. Nathan has the answer. Remember, you're going to tell me how much the red flower is worth, the blue flower, the yellow flower, and then the sum. Ariana, Christopher, and Eric, when you've got it, raise your hand in teams. Do we think we have the answer? Christopher, you got it? Eric, you got it? No. Eric. Christopher, you think you have it. Eric.
I was working on the
Oh, you're still working on that. Can you do the flowers?
Yeah.
Can we do the flowers real quick? I like to end with a little puzzle.
I can't even see it on my screen for some reason.
You can't see it on your screen. Oh no, that's terrible.
No.
That's pitiful. Well, you can leave and come back, or you can just watch the video. Maybe. It's up to you. How much is the red flower worth?
20.
Oh, never mind. I can see it.
Oh, you can see red is 20. How much is the blue flower worth?
5.
5.
How much is the yellow flower worth?
1.
It is. Did y'all see that was 2 flowers? 2 yellows. Okay, so then if I substitute in, I have yellow plus red plus blue gives me what?
26.
26.
That is correct. Yay. I'm leaving you with flowers. Okay, so go ahead, think about the third finite difference, fourth finite difference, see if you can come up with a pattern, and then I'm going to show you the shortcut tomorrow and tell you the quick way. Then we'll begin with a little graph. We'll graph one of these quadratic functions, and then we're going to do transformations. So have a wonderful rest of your day, and I will see you tomorrow.
Bye, Miss.
Bye.
Bye, Miss. Have a good day.
You too. Bye-bye.
Bye, Miss.
Bye.
Bye, miss.
Bye.